Hello, everyone. Welcome back to our lectures today. We will be talking about introduction to enzymes and enzyme mechanism. So we'll look at what enzyme is and then their general characteristics, and then we're going to look at different mechanisms in which the enzyme uses to function. Now, I have a beautiful picture for you here. The beautiful picture I have here is from again, I want to give credit to few softwares that I used in making a lot of my videos. The BioRender, particularly, I used a lot of their free version. BioRender, I used it to create a lot of images. I used MoleView and then BioVia and a lot of other free software that I've used in enhancing the creation of my lecture notes and videos, and I owe them a great deal of thanks. All right, let's get into it. So this picture, again, like I got this from, this is from BioRender, is a generic enzyme, because we're talking about enzyme today, generic enzyme. And I'm just trying, we're still going to see this picture as we get into the class. I'm just trying to show you this groove you see here. This groove is actually the active site of an enzyme. The active site is a portion of an enzyme that binds with the substrate and initiate the catalysis. And inside this active site is where you have the functional groups that actually involves in that biochemical process of transforming a substrate into a product. A substrate is the enzyme reactant. And let's get into this. It will be an interesting one. We have 4 learning objectives here. They include, number 1, we're going to describe the general characteristics of enzymes. 2, we'll describe the enzyme specificity. We'll understand what this means with examples, and then we'll describe the general enzyme mechanism or catalysis. If you don't want to use the word mechanism, you can always use catalysis. I'll try to interchangeably use those words. You can use enzyme mechanism or catalysis. And finally, we'll describe the theories of enzyme mechanisms or enzyme catalysis. If you say enzyme mechanisms, you can also, or enzyme catalysis. Anyone you want to use, that's okay. It doesn't matter. Like I said, this, either you say the enzyme mechanism or enzyme catalysis. All right, let's immediately take it off. Before we do that, I have a beautiful quote here from an inspiring story of a slave that rose up and became a strong political activist and a strong human right individual and an abolitionist. What does she have to say? She says, "Every great dream begins with a dreamer. Always remember, you have within you the strength, the patience, and the passion to reach for the stars to change the world." Harriet Tubman. No matter your condition, no matter what state you were born. Harriet Tubman was an American abolitionist and political activist. She was born into slavery. She escaped slavery and helped rescue more than 70 slaves, including family and friends. And she did that by setting up what was then called safe houses, or better known as underground rest, to do that. Despite her condition, she found a way to contribute and achieve her dream of contributing to the end of slavery. And I challenge you today, anybody, no matter your condition, can do something different in this world and make a strong impact. All right, let's immediately take off the lecture from here. What are enzymes? Enzymes are biological catalysts. They're usually proteins. And what are catalysts themselves? Remember, like we did in the introductory class before this level of class, catalysts, what they actually do is that they speed up the rate of chemical reaction by lowering the activation energy of a reaction. And what do? They allow reactions to achieve equilibrium more rapidly or faster. That's exactly what catalysts do. So in this case, these are now biological catalysts because they are mainly proteins, and proteins are biomolecules. I talked about that already. So what do they do? What they do now, this is a typical enzyme catalyzed reaction. We're going to see why enzymes are much more efficient than ordinary inorganic catalysts, because they are very efficient. They have enormous catalytic ability. So this is reaction, the energy profile of, this is an energy profile of an enzyme catalyzed reaction, the energy profile diagram of an enzyme catalyzed reaction. What is happening here? Now, you see, without an enzyme, the uncatalyzed reaction, of course, at the pinnacle here is the activated complex or the transition state. Let me use the word transition state. This is the transition state. transition state. Now, look at how high this mountain is. And a reactant has to cross this mountain to form the product. Now, if you measure this mountain, okay, let's try to measure this mountain. How far is it? If you measure it from here, look at how far the reactant need to travel before they become the product. That is very high. What does an enzyme do? An enzyme comes and cuts this thing down into a manageable size, into a manageable hill, so that the reactants can easily, they don't have to get through this side, they'll just get through this shortcut and then form product. So what the enzyme does, or what every catalyst does, is to provide a shortcut for a reaction to be achieved much quicker. And that takes us to the characteristics of enzyme. What makes enzymes different from the rest of the inorganic catalysts? Number one, enzymes possess tremendous catalytic ability. They have strong catalytic ability, tremendous, great catalytic ability that is much more greater than the inorganic catalyst. To what extent? They increase the speed or the rate of a reaction up to a factor of about 10 raised to power 20 compared to the uncatalyzed reaction. Can you see that? So that is how much they actually do this job. The rate at which they push this catalysis is very tremendous. And in fact, this beats down what you see for inorganic catalysts. Number two, now they are highly specific in the reactions they catalyze. They are highly specific in reactions they catalyze and the substrates that are involved. Now, enzymes are highly specific. They have like division of labor. A particular enzyme will catalyze a particular type of reaction or a particular type of structurally related substrate. It cannot overlap. Enzymes are highly regulated. Highly regulated. Another character, the third one. Now, enzymes are intrinsically controlled and regulated, either by mechanisms involving their actions or involving the product and the substrate. So that at no point in time will an enzyme have to produce a product that is too much or that is not needed in the body. When such a condition begins to occur, that means there is a serious pathology in the biochemical pathway, or a serious problem rather in the biochemical pathway or in the system, in the living system. Now again, like I said earlier, there are proteins in nature. There are proteins in nature that are usually proteins, except but a few self-splicing RNAs. We call them the ribozymes, which usually see them, these ribozymes are usually seen in DNA, in the replication process. That is only when we see them. But apart from this, every other enzymes we know in nature are proteins. Then the next one, they are not consumed at the end of the reaction. They are not consumed at the end of the reaction. Enzymes are not consumed. Nothing happens to them. The same way they get into the reaction, they come out without being touched. That is another important ability of enzymes. Again, they perform their catalytic functions with the help of non-protein components. And these non-protein components are called cofactors. Cofactors are either ions or organic molecules like vitamins that help enzymes to perform its function. So enzymes at times don't do this work alone. They need the help of these cofactors. And finally, every enzyme has an active site. An active site is that portion of enzyme where it uses to bind the substrate and initiate catalysis. Inside the active site is where you have the functional groups, which the enzyme uses to interact with the substrate and initiate those biochemical reactions. So these are the characteristics of enzymes. So let's now begin to, before we continue talking about enzymes, let's introduce a few terminologies that we need to know, because some of these terminologies I've already used them, but I'll keep using them until the end of this enzyme lecture. The first one I want to introduce is the substrate. The substrate is the reactant of an enzyme. It is the reactant of an enzyme. It is that substance that the enzyme interacts with, and then from there it converts it to the product. So the enzyme, of course, you start with the substrate. The enzyme will act on this substrate and convert it to the product. So that enzyme's reactant has a special name, unlike what we have in inorganic chemistry. It's called the substrate. Cofactors. What are cofactors? Cofactors are non-protein molecules or ions that are required by enzymes for catalysis. Those non-protein molecules that help enzyme to do its job of catalysis are what we call the cofactors. They are non-protein molecules or ions. So they could be molecules, organic molecules, or ions. So what are coenzymes? Coenzymes are organic cofactors. Those organic cofactors are what we call coenzymes. And they're mostly derived from vitamins. And that's why vitamins are very, very important for the normal functioning of the body. Specificity. What is specificity? The capacity of an enzyme to choose the exact substrate from a group of structurally related molecules or stereoisomers. So like I said earlier, enzymes are highly specific. So the ability for it to choose, to make that choice, that this is a particular substrate or a particular reaction that I will catalyze, is what we call the specificity of an enzyme. And again, I've talked about a couple of times the active site already. The active site is the portion of an enzyme where the substrate is bound and then for catalysis to occur. And like I said, the active site has all the functional groups of that interacts with the substrate and initiate the reaction. And finally, the last one we're going to talk about is regulation or control. Regulation or control is intrinsic mechanisms that control the activity of enzymes or the amount of product they produce. So enzymes are not out of whack like crazy guy. They are controlled because if they go out of whack, bad things actually happen in the body. So we now begin to break down different types of specificity of an enzyme. Now, there are three types of enzyme specificity we're going to be talking about. Number one, the absolute specificity. In this case, an enzyme catalyzes the reaction of one unique substrate. It doesn't want to catalyze any other substrate. The enzyme says, okay, I want to do this particular substrate and convert it to a particular product. A good example here is glucokinase. Glucokinase is an enzyme that catalyzes the first reaction of glycolysis, whereby glucose is converted to glucose 6-phosphate. Now, what actually happens here is that glucokinase only catalyzes the phosphorylation of glucose. It is not going to catalyze the phosphorylation of any other hexose, whether it is fructose or whether it is galactose. It has no interest. Glucokinase, and it has it in its name, wants only catalyze the phosphorylation of glucose and convert it to glucose 6-phosphate. Remember, this P here means phosphate. Now, what about relative specificity? Relative specificity is the ability of an enzyme to catalyze a reaction of a structurally related group of substrate to give a structurally related group of product. So here now, in absolute, just one. But in relative specificity, they are catalyzing a group that are structurally related in some way. Now, a good example here is hexokinase. Now, hexokinase, again, is a reaction, is an enzyme that catalyzes the conversion of the three hexoses, glucose, fructose, or galactose, from the hexose to a phosphorylated hexose. So it can catalyze glucose to glucose 6-phosphate. It can catalyze fructose to fructose 6-phosphate. It can catalyze galactose to galactose 6-phosphate. Because all these three are all hexoses. And you see from the name, it's a hexose. So it catalyzes the phosphorylation of all hexoses, whether it is glucose, whether it is fructose, and whether it is galactose. And the last one is the stereospecificity. In this case, enzymes catalyzes a reaction for a unique stereoisomer instead of the other. Remember, stereoisomers are the D and L isomer. Enzyme has the ability to recognize a particular isomer, and this is actually very important in the body. Most enzymes only catalyze a particular specific isomer instead of the other. A good example here is that most enzymes, like the amylases, are digestive enzymes that break down carbohydrate in the digestive system. And other enzymes other carbohydrate metabolic enzymes are only specific for the D isomer of glucose and not the L isomer. For the carbohydrate, the D isomer is what the enzymes in the body wants to catalyze. Now, let me tell you the opposite. What about amino acid and proteins? For the amino acid and proteins, the L isomer is what the enzymes of the body, like the peptidases, want to do what? Want to catalyze. So, enzyme is specific for a particular stereoisomer. It doesn't usually say, okay, I'm in charge of all stereoisomers. It doesn't do that at all. We now go to the next concept. We need to talk about enzyme cofactors. Enzyme cofactors are non-protein molecules, like I said earlier, or ions that help an enzyme in its catalytic action. For enzyme to function, these are the enzyme helpers, help enzyme to do the job. And they can be either the coenzymes or the inorganic ions. Now, the coenzymes are the organic cofactors, and most times they are derived from, most of them are derived from the vitamins and include the NADH. This means nicotinamide adenine dinucleotide. This is the reduced form. The FADH2 means flavin adenine dinucleotide. That's the reduced form. Biotin. FMN means flavin mononucleotide. The tetrahydrofolate THF, and all the rest of them. There are a lot of these particular vitamin derivatives or coenzymes that help different enzymes depending on the metabolic pathway to do its job. Now, and you usually find them at the enzyme's active site, where they are staying there to help the enzyme to do its job, because the enzyme job is only done at the active site. Now, the inorganic ions are mostly metal ions, and they include mainly the magnesium ion, zinc ion, and even iron 2 ion. Now, what is an apoenzyme? An apoenzyme is a catalytically inactive protein or enzyme without a cofactor. Now, let me tell you this. Most enzymes are typically inactive without their cofactors. Remember, the cofactors are the inorganic ions or the coenzymes. So they remain totally inactive. The apoenzyme is a catalytically inactive protein without the cofactor. Now, however, if you add a cofactor to the apoenzyme, you form the haloenzyme. A haloenzyme is a catalytically active protein with its cofactor. So if you combine, let me use a different color. If you combine an apoenzyme plus its cofactor, you have a haloenzyme. And haloenzyme is an active enzyme that will actually engage in catalysis or catalytic activity. Now, however, tightly bound cofactors are called prosthetic group. Remember when I told you earlier when we did proteins, we said some enzymes, we talked about the example of a hemoglobin that has a prosthetic group of Hep. So when these particular cofactors are tightly bound, intimately bound all the time to an enzyme or to a protein, we call them prosthetic group. However, some of them are not always bound. Some of them are only there when the enzyme needs to do its catalytic activity. However, some other ones, like the hem, is always intimately all the time bound to what? The hemoglobin, for it to be able to do its what? Job as an oxygen carrier. When I go to mechanism of action of enzymes, or mechanism of action of enzyme, or you can say mechanism of enzyme action or catalysis. You can use the mechanism of action of enzyme action, MOA. Most times I use MOA, mechanism of action, or catalysis. Anyone works. So all enzymes, like I said earlier, have active sites. That's an important characteristic of enzymes. Now, it is at this active site that catalysis occur. Remember, catalysis occur at the active site. Occur here. That is where catalysis occur. Now, how does this catalysis start? Binding of a substrate occurs through electrostatic interaction. There are 3 electrostatic interactions at the active site. They include the hydrophobic interaction, or you say London dispersion forces, the hydrogen bonding, and or the ionic bonding. Remember, one thing common about the electrostatic. Electrostatic means it involves some form of non-permanent bonding. It's not a covalent bonding. The ones that bring about covalent bonding are going to be poisons and would deactivate the enzyme. So it has to be these electrostatic interactions that are involved. Now, so what happens? So enzyme substrate complex, ES complex, is for enzyme is E, substrate is S. So the enzyme substrate complex is formed when a substrate binds to an enzyme. Now, after this binding, it results to the conversion of this substrate to what? The product. At the moment the enzyme binds to the substrate through the active site, it now does some series of chemical reactions and converts the substrate, which is S, to product P. Now, chemical transformations of the substrate that occurs in the active site is facilitated by the enzyme functional groups. The enzyme itself have the functional groups that are involved in doing this interaction. It is at that functional groups that it interacts with the substrate through hydrophobic interaction, hydrogen bonding, and or ionic bonding. Now, after conversion, the product itself is released from the active site of the enzyme, and the enzyme itself is also released free. And the free enzyme it's not ready for another action. Like I said again, I showed you this thing in the introduction page. This is a generic enzyme. Now this enzyme has a groove. It is this groove that is called the active site of enzyme, and it is inside this groove is where you have the functional group of the enzyme. And the functional groups of enzyme are those groups that interact with the substrate through those three electrostatic interactions, the hydrophobic interaction, hydrogen bonding, and ionic bonding. So this groove, so every enzyme have this small groove, and this groove is just a small portion of the enzyme, but actually determines whatever that happens in that enzyme. So I have a little schematics to show you here about the enzyme catalysis or mechanism of action. Now this is an enzyme here, E. An enzyme, first of all, interact with the substrate, and they form this intermediate. This intermediate is actually what we will call in inorganic catalyst the activation complex, the temporary activation complex. Although it's a little bit more than this, I'm going to show you another scheme, another flowchart or diagram in the next page. Now, the moment this thing happens, the transformation occurs, and the transformation that occurs is that this product will now be converted to, this substrate will be converted to product, and the product is still bound to the enzyme, and finally, both of them will now be released. So the enzyme will now be released, and the product is released. And I have a good example here. Maltase. Maltase is a digestive enzyme that acts on maltose. Look at what happens here. Now, this is the enzyme E. This is the substrate, maltose. It interacts with maltose, and what happens? And forms the maltase-maltose complex. Like I start again. The maltase is the enzyme. It interacts with the maltose, which is the substrate, to form the maltase-maltose complex, which is the ES complex. Now, what happens? The ES complex undergoes those transformations to become the intermediate, including formation of the transition state. And finally, what happens? It results to the formation of the product and the release of the enzyme. So after those transformations takes place within itself, I don't like what I wrote there. Let me just make it clearer. This ES complex. Like I was saying, so what happens? The moment those transformations, the transformation is taking place here, in the active site, using those functional groups. The moment those transformation takes place and convert this maltose to glucose and glucose, two glucose molecules, what happens? The maltase is released and the product, two glucose molecules, are released. So this is the summary of the schematic summary of the mechanism of action of an enzyme. It could be more than that. In much more higher biochemistry class, this is how we put it. This is an energy profile for the enzyme mechanism of action or catalysis. Look at what happens. The enzyme and substrate comes in, of course, they are free in the first place. They combine together. When they combine together, of course, this is actually in a higher energy. Look at what happens. The formation of this guy forms a little bump, but now takes a dip in a lower energy. This is the enzyme substrate complex having formed. The moment they form, chemical transformation will begin to take place. So you're going to form, so this substrate is going to be converted to an intermediate, which is the transition state, which is the intermediate. So this now will be converted to transition state. Before that happens, it's going to bump up again because there's energy is used in the active site to do those transformations. That energy is shown by this big bump in energy here. And now you now convert this substrate to the transition state. But it is still bound to the enzyme. After that transformation occurs, what happens? The enzyme, this is now converted to product. And then finally, the enzyme is now released and the product itself. So this is enzyme product. And the difference between this ES complex and the ES transition state complex is what gives you the activation energy, which is that particular barrier that the enzyme will have to cut. If the enzyme is not here, right, this particular bump is actually going to be much more higher than this. Look, it's going to be actually much more higher than this. But the enzyme comes to cut it down for this reaction to proceed well. So like I said, this energy, delta G, is the activation energy, which is the energy required for this reaction to take place. And like I said again, this energy here involving the enzyme is smaller. When the enzyme is not there, the bump is actually going to be much more high. And that is what is actually shown in these schematics down there. The enzyme combines with this guy, forms the ES complex. The ES complex now undergoes those transformations to form the enzyme transition state complex. The enzyme transition continues those transformations to form the product and releasing the enzyme again. And like I said, if you want to label it, this will be the transition state. This is actually the transition state, which is the highest energy level point before the products are actually formed. And the last thing we'll be talking about in this class is the theories of enzyme actions. There are two main theories of enzyme actions in the early understanding of enzymes. So we're going to look at them. Now, the first one is what we call the lock and key. Now, the lock and key postulates that the substrate binds to the active site of an enzyme with a complementary shape as a key fits into a lock. You know how a key fits, you get a particular perfect lock, you get a key that will fit it in completely to unlock it. Now, that is exactly what we call it, the lock and key model. So now, here, it implies that the enzyme is fixed or rigid in shape. That's what it's trying to say. But it's not true. Enzymes are protein. They're very flexible. They're very pliable. They're not just rigid as this implies. Now, so the enzyme active site is actually flexible in contrast to this theory. So we're going to see the second one, which will be the modification of this. So if you look at this, my picture again, I got this from, I used biorender to design this. Now, this is the substrate, having a shape that will fit into the enzyme. See, this shape and this is complementary. And if this goes and fits in here, it forms the ES. So this is the substrate, this is the enzyme. It comes here to form the ES. This is the E and the substrate. So a key fits into the extra shape of a lock. This is the what? The lock and key model. But however, this has a limitation because it assumes that the enzyme is rigid. However, enzymes are not rigid. So the second theory is a modification of this first one. We call it the induced-fit model. The induced-fit model is that postulates that the conformation of the active site of an enzyme changes to accommodate the incoming substrate. And this change only takes place when what? When the substrate has bound to the enzyme. So the active site has a shape that becomes only complementary when the substrate have bound to it. And like I said, this is the modification of the lock and key. It's the modification of lock and key. Let's see what is happening here. Now look at this enzyme. This shape looks like a kind of rectangle. Let me say a rectangle, that shape, right? And then look at this shape here. This shape looks like an arc. This is an arc. Now, so the shape is not complementary. Now look at what happens. The moment this guy comes to bind with this guy, look at what happens here. This enzyme shape now changes from this arc to another rectangular shape and it becomes complementary. So the only time it becomes complementary is when the interaction happens and the enzyme adjusts and moves itself because it's very flexible to adjust itself to what? To the type or the shape of the substrate that binds to it, forming the what? The enzyme substrate complex. So again, this particular theory assumes that enzyme itself is very flexible. And this actually reflects what the enzyme does with other further understanding of the enzyme mechanisms. And having said that, we've come to the end of this lecture. Thank you once again for listening. Bye at this point. I know I already said goodbye, but something that I need to say before I actually leave finally is, please, this last slide, I know you're not going to see, this is not going to work in the video, in the YouTube video, but please go to your note and make sure that you watch these two video animations, the enzyme mechanism of action. Please try to watch these two video animations. They're going to help you to broaden your understanding about enzymes action. So again, thank you for listening. Bye.